Hello. In today's videos, I'm going to explain a little about the format of the data products. I recall that this was extensively explained in the article, but there are some new extensions into the output of DAP data products that I think is worth mentioning. Um, I hope this video is going to be shorter than previous ones because it's considerably, it should be faster uh, to describe this format, especially if you have read the article. Um, I'm trying to show you where in the article this is described. So if you go to the DAP article, in here, it's describe what's the output format. Is this one basically what you have when you run the DAP? The main result is a fit file with different extensions. The first extension is a primary header that is inherited from the LVM as frame. So basically, it's the same header that you may find in the as output of the data reduction pipeline, just for traceability to trace back what from which data the analysis has been done. And then we have a position table. I'm going to explain the columns. And then we have an RCP extension. The rest are tables that fits table that can be read with different tools. I will show you that you can read them with TOPCAT and you can read it with Python. And in each of them are included different data products. The first is the position table. Again, this is inherited from the data reduction pipeline. The only difference that in here it's included only the signs fibers, so it's everything that is not signed is trimmed out. And it's basically the position table that has been derived by the data reduction process. Then we have the RCP, that is the average properties of the stellar content. The average, this is a collapsing of in the PDF. So basically, it's the average temperature and log gravity and metallicity and alpha enhancement. Then we have the coefficient of the decomposition that of the composition in these RCPs, in the result stellar populations, in the templates. Then we have the properties derived from the parametric analysis of the emission lines. We have three tables: the blue, red, and infrared, where we split the results from the analysis of the emission lines using the non-parametric method. And finally, we have the info, that is a table where is stored all the entries in the configuration file that I'm going to explain other day. So this is what we publish, but if you now go to the current DAP file, that the way that this is generated, this is the label that you put in the when you run the LVM-DAP script. Remember, when you run it, it's requested this label. This label is exactly what is used to write the output. And then we have dap.fits. It's compressed. And now you will see that besides the extensions that are described in the article, there are new extensions. There is a new extension, the PMKL. This is for the. Remember that now we have two analysis with the parametric fitting of the emission lines. This is the result of the second one. The lines that are analyzed are the same that in the previous one, but in the first they suggest using the result from the analysis in the iterative process where the stellar content and the emission lines are fitted, and this is afterwards when it's subtracted the best model of the stellar content and it's run again this analysis. Then we have the mission lines with the chi-square that it was and the chi-square and the velocity corrected for the instrumental the line of sight profile of the instrumental resolution, and it's provided just in kilometers per second plus the chi-square of the fitting. This is an average of the chi-squares for all the emission lines. That this is a way to weight the quality of the fitting, and then the info extension is the same as before. It's the content of the YARN file of the configuration file. So all these extensions, as you can see, apart from the primary, are fits tables. So you can read them if you want to make a quick visualization without not dealing with any programming. You can read them with TOPCAT. So TOPCAT is going to identify the different extensions, okay? And of course, the 0, that is the header, is not available anymore. So the one will be the position table, and it's identified here, position table. So you can easily identify what's the content. It's an ID that identifies the fiber, and this ID is something that I constructed for uniquely identify the fiber and the pointing. So this will be the ID of the tile dot the ID of the fiber, and the number is not going from 1 to incrementally because it has trimmed the non-signed ones. And this is a very useful way, it's explained in the article, to store this information, because when you can create mosaics just stacking the tables, and the ID will always be referred to a tile plus a tile, pointing an exposure, better to say, of a certain tile plus a fiber. So you can create mosaics very quickly. Let's see if we can show you later. Then there are access and declination, and this is this ID decomposing fiber ID and exposure. So it's a kind of repeating this index, but it's quite useful if you want to sort things like in a database, or if you want to identify from which exposure the data has been taken. Then we have the RSCP extension. Again, the ID is the primary key. So when you want to, if you want to join tables, this is the one that you can do. You can do that in TOPCAT. I'm not going to do that, but that can be done in well, we can actually do it. We can. Let's see, very much. No, so no, that's not. It's concatenate tables. That will be the. Well, in the joins, I will figure out later how to do that. But that's there is a way of doing this matching using a certain algorithm. I will show you later on, but that's not the primary reason of this video. So it's to explain the content and then to show how it can be handled with Python. And I can prepare a separate video of how to join that in TOPCAT if someone wants. Sorry, wants to use it. For the position table, we can make a very simple. No, that one. No, sorry. Well, I could have used that one, but No, that's not the table I want. I want this one. I can present just the position table with the correct orientation, and the holes correspond to fibers that were broken and low quality and so on. Okay, the second extension of the RCP includes the key square of the fitting. That's the key square of the complete fitting, and I could not give too much weight on this parameter until we have a good estimation of the errors. And then we have for each parameter included in the RCP catalog, the average property. So the temperature with the error, the logarithm, the error. When the error is zero, that basically means that it has a very low, the signal to it was poor, and it has selected just 1 star, so there is no distribution. And since assigned just a single star, it provides with no errors in the Monte Carlo process, because all the time fit into the same star. So that should not be interpreted as a very good quality, as you can see in the key square. To guess if this is not the quality of this fitting, it's better to check the flux, the median flux of the spectra and the error. And these two values are going to tell you what's the signal to noise. And as you can see, the signal to noise is pretty poor in many cases for the continuum. This is the median flux at a certain Weldon range, and this standard deviation that is within this Weldon range, that is around 5,000 angstroms. And when the signal to noise is very low, the code does not make a decomposition, just assigns to the star that is more similar to the observed spectra, and that's why there is zeros everywhere. So I don't know if we will have some, like here, this is an example where you have an error. You will see that when you have an error, basically the signal to noise, it's higher. You see here, this is a signal, that's the noise. So in here, it was able to decompose the stellar population. So do not interpret zero as actually no error. So it's just the contrary. Okay. Well, we have the light-weighted values, and we have the mass-weighted values. These mass-weighted values and the mass-to-light ratio, and the table with the mass now is a filler. Why? Because actually we don't know we don't know how to assign the masses to the recipes so far. So it's included here for future developments, but do not trust on that parameters. Just trust on the light average ones. Well, that's the second station, the RCPs. Third extension, this includes the weight, the coefficient of the decomposition, and of course, this table have for each fiber a number of rows that correspond to the number of RCPs in the template. So if we are using 108 108 CCPs or 24 CCPs, you have to multiply the number of fibers by the number of CCPs. So you can check in here that there are many entries that share the same ID because they correspond to the same fiber but to different CCPs. And this is the index, the value RCP is the index of the RCCP in the template. So this runs from 0 to 107. So because we have 108 RCCPs, and then it jumps to the next fiber and it starts to 0. And this is the weight, since I told you before that in most of the cases for this particular data set, that is the Helix Nebula, the continuum is swimming in the noise. It has assigned just to one single star, so all the coefficients should be zero, but one of them, this one. So this is a star that is the program indicates that is more similar to the continuum, and they say you that that's when you have a very low signal to noise. And only when you have enough signal to noise, if you check in here the fiber that we have identified with an error, this is the fiber, for example, 8, well, that's quite a large number to look for. Even this one, 514, let's see, well, 519. 519. Maybe there is no other one. It's 519. So we have to look for 519 here. 519, 508, 519. Okay. So for the 519, that is this one, you will see that the weight, that's mass, light weighted at the same way that I said before, around 5,000 angstroms. So the contribution of this particular star is just 1%. And here in the bottom, there will be other stars that contribute like 10%, 0.3%, 2%, 2.5%. So these are the weighted the mix the RCCPs to produce the model of the underlying stellar population, and the average of the temperature multiplied by this weight and sum. The sum is of the coefficients is 1 because it's scaled to 1. Will correspond to the value that enters in this table, in the RCP table. Again, I have to find it. So this temperature here is the average of the temperatures of each star multiplied by the weight in the composition included in the additional table. This table, the coefficient table, can be used also to generate PDFs, because these coefficients can be multiplied by the PDF of each individual RCCP. Remember that an RCCP has not, it may have an average temperature, but it's in reality what it has is a probability distribution function. And I will show you how to generate that from using the RCCP template. There is an extension in the RCP template that is the PDF of each individual star. And using these coefficients, you can generate the PDF of the composition of a particular science spectra. Okay. The next extensions included the table where it's written the results of the emission lines, and in here you can see that for each fiber you have different entries: the emission lines, the wavelength of the emission line, the flux, the error, the velocity dispersion in angstrom non-corrective for the instrumental one, the error, the velocity, and the error. So this is the format. Again, there are different entries for the same fiber because there are different emission lines that has been fitted using the Gaussian modeling. And now we have three extensions that correspond to the B, R, and I range, so the three range of the spectrographs. Let's check this one, for instance. The content is the same. It's the result from the non-parametric analysis of the emission lines. And in here, the format is slightly different. For each fiber, we have a row, and in this row, we have each column identified a certain line and identify the flux, underscore the name of the line, underscore the name of the wavelength. These are all the lines, and then you will see that there is a another entry for the velocities, and another entries for the dispersion, another entries for the equivalent widths, and then another entries for the errors of the parameters. Okay, so this is the format where it's stored. So instead of having different an entry for each line, we have an entry for each fiber, and we have different parameters that are read, that are filled. Sorry. The three extensions B, R, and I have the same format. Finally, we have the new extension where it's described the result of the fitting with Gaussians for the strong emission lines. And in here, the format is exactly the same as the extension where we have, that I described before, the PM lines. So it's exactly the same, totally equivalent. So for each fiber, we have different entries, and these entries correspond to the different analyzed emission lines, and well, it's exactly the same format. Now we have the A-line sigma chi square, and this this extension comprise just the velocity dispersion corrected for the instrumental ones in kilometers per second, for the emission lines analyzed using the non-parametric procedure. And apart from that, you have the chi-square of each of these modeling. Okay, it's not only for the parametric ones. It's for the non-parametric ones. It's also include the non-parametric ones that are this PA key for the second iteration, and the PE should be somewhere for the parametric ones. For the first iteration and the second iteration with the chi-square. So it's quite a large table, but from here you can check the quality of the fitting and the modeling, and see if it's useful for your science case. Finally, we have the average chi-squares for each emission lines, and the instrumental dispersion. This is just for a quality check. So average through the field of view. So in here you can guess which lines have a good quality, which ones have a bad quality in the fitting, average through the entire field of view. And finally, we have the info that, as I told before, it's basically the content of the YARN file that I will explain in a separate video. So this is these are basically the content of the output file, and I'm going to stop this video in here. I promise to keep this video shorter. And in the next video, what we are going to do is to read this output with a Python notebook that is included in the DAP, that distribution that basically rearrange all these tables in a single table in a more convenient way, making all the joins, and create it's a table where we will have a row for each fiber, and with that we can plot comparing line ratios, making maps, and so on. So that I will leave for another video.